We're going to go through diffusion relatively quickly. A lot of times when we think about diffusion, we think about atoms or molecules in the air moving through a fluid such as air or water. What we're talking about, again, in material science, is we're talking about things in a solid. So diffusion can still happen. Atoms or molecules can move through a solid, and that's what we're going to be discussing. Remember, solid materials, even though we think of them as hard, impenetrable, they're really just a bunch of really, really small atoms or molecules that are bonded together, and there's a lot of empty space. There's empty space between them because when we model them as the hard spheres, like when we did our packing density, we also have to remember that really they're just protons and neutrons at the center of the nucleus, and there's just electron clouds around there. We have to remember that the bonds are vibrating and the atoms are moving around slightly and vibrating, moving, stretching, compressing, and so there is a lot of empty space there for diffusion to happen. There are two types that we're going to discuss. We're going to talk about non-steady state just briefly, and then we'll get into steady state diffusion with some equations that go along with that. Let's say, though, I have just a membrane, some material, and we'll go with a thin material here. It doesn't matter what it is, it's just some material, and on one side of the material, I have a concentration 1 of something, and let's say that that concentration is about this tall, this high. So kind of using this as a graph here, and I have the other side, and I have concentration 2 on the other side, and it is also about that high. So they have the same concentration. We are going to get some diffusion, but the diffusion is going to be completely flat through here. So whatever this is, let's say that this is hydrogen gas on both sides. Both sides have a high concentration of hydrogen gas. They both have the same, which means there's going to be some hydrogen gas inside my material that's separating them. We could have a picture where, again, I have some material. We'll use hydrogen again. And I have some concentration over here. But let's say on the other side now, I have a low concentration. The question here is, what's going to happen? Well, both of them have hydrogen gas. And so hydrogen is going to try to get through the material in both directions. But coming from the left, there's a higher concentration, more of it's able to get through or trying to get through, where on the right we have less of it, and so it's less of it's trying to get through. All right, so I'm going to say, draw this out one more time. I have concentration 1, which is high. I have concentration 2, which is low. We have our hydrogen gas that's trying to get through. And initially what's going to happen is a lot of it wants to try to get through, but it's not going to be able to get through very far because in liquid, in air, diffusion happens relatively quickly. In a solid material, it happens much more slowly. So maybe on the very surface, on the left-hand side of my picture here, there is a somewhat high concentration. But as we penetrate, as we penetrate, it's going to drop relatively quickly. And so we end up with something that looks kind of like a nice curve here. Over some time, we're going to get a new picture, and it's going to start flattening out a little bit, and then a little bit more time happens. We keep diffusing mostly from the left to the right. Now remember, some of it's trying to work back the other way. But eventually what's going to happen is I'm going to get the picture where we get a linear concentration gradient through here. It's not going to change. It's going to stay completely linear like this. But we need to understand that hydrogen is still moving through here. So some hydrogen is still moving this way. A tiny bit of hydrogen might be coming this way. And the material, it's still allowing hydrogen to move through, but it's come to an equilibrium. So this first picture here, the one on the left, this is called non-steady state, and even into this second one here, these are non-steady state or transient diffusion. The one on the right, once we reach an equilibrium, we call that steady state diffusion. Steady state diffusion, once we have steady state diffusion, time really isn't a factor anymore because we can let it sit theoretically forever, and it's always going to stay with this concentration gradient. With the ones that are non-steady state, time is going to be a huge issue, and so we're going to really have to have two equations here. The one that we're going to talk about is going to be the steady state. Simpler, it's a little bit more easy to model. If we wanted to talk about transient or non-steady state, we could do that as well. That would be a second equation, which we're not going to be getting into quite yet, though. All right, so what we're going to do is we're going to talk about Fick's first law, and Fick's first law is about steady state diffusion. I have my picture here. What I'm going to do is I'm going to draw kind of a graph of what we've just done. I have high concentration, concentration 1, and I'm going to have a low concentration, concentration 2. Some of the stuff from concentration 1 is going to move over to concentration 2, and some of the stuff from concentration 2 is going to work its way back. We could actually divide this up maybe into much smaller bins or segments. And so what I'd have is, let's say that for this higher concentration, let's say between each bin, 10 molecules or 10 atoms want to move over to the bin to the right, but it doesn't care what the difference between right and left is, so we also have 10 that move to the left. Okay, all that's fine. The concentration is not going to change in the concentration 1 section. Same thing is happening over here in concentration 2. It's much, much smaller, so maybe we only have one molecular atom that wants to move from one bin to the next. But again, concentration 2 stays pretty much the same. What happens, though, is where those two meet. Where those two meet, again, concentration 2 wants to send one of its atoms over into concentration 1, but concentration 2 wants to send over 10 into concentration 2. And so really what we have is we have a net of 9 atoms or molecules moving over to the right. We allow this to keep happening. There is going to be movement. It's going to keep moving, and eventually we're going to get a picture. Again, we're going to assume that we've allowed time to pass because we want to get time kind of out of the picture here. After we have enough time passing, we're going to kind of have this stair step where all these bins have kind of come to an equilibrium. I let it keep happening, and I'm going to get this straight line. That's the same straight line that we drew up here on the right. Now I want to write out Fick's first law equation, and I want to put out, give you guys what the variables and stuff for that are. So Fick's first law is J equals negative D, the change in concentration over the change in X. Those could just be simply change ofs. I don't necessarily need partials. I could do just deltas. Either one of those work for this because it's a pretty basic equation once we get everything figured out. So J is our flux, and flux is just things moving. So it's our mass that's moving through. And the dimensions for that are amount per area time. So I have an amount of atoms, and they're moving through a certain area of my material or membrane per time. I have D, and D is my area. Well, first it's my diffusion coefficient or my diffusivity. And what the diffusivity is it is an area over time. My C is my concentration. And my concentration is my amount per volume. So how much stuff, how many molecules do I have in any given volume? If my volume is bigger, I have a smaller concentration. And my X is my position. It's my length into or through my material. That's my length. So this here is for steady state. Nice, simple equation. Once I get everything figured out that I need, I can plug numbers in, and it's pretty good. If I wanted to deal with my transient or my non-steady state, we would use Fick's second law, and it gets quite a bit more complicated because we have to have how my gradient here, how my concentration gradient is moving with time. If we really break this down right now, this right here is my slope. It's my concentration over my position. So it's my rise over my run. And if we think about, well, if it's not constant, right? So here is our not constant. We have a changing slope. It's going to get more difficult, and that's going to be changing with time. I just want to let you guys know that there is a second law out there. It is a little bit more complicated. It deals with non-steady state, but it can be useful. I want to talk about activated processes really quick. Activated processes, some examples are the movement of defects and diffusion. That's what we're talking about today. Movement of charge carriers, that's going to be important, especially when talking about semiconductors, and nucleation, how things nucleate. This is just going to be a quick picture. I'm going to have energy. And if I have a picture of my atoms that looks something like this, and then later on, a picture of my atoms that look like this, and I have an interstitial atom there. It starts off on the left, but by the time it gets to my right, it is in the right. At some point, it had to be able to squeeze through those two atoms. It had to diffuse through, it had to move somehow. And so there had to be a picture somewhere where it was between here at some point. So my energy level would be low when it was at its interstitial site. It's nice and happy. It's low again once it's in the other interstitial site. But when it had to squeeze between these atoms, remember, atoms are vibrating, they're moving, something's got to happen. Energy's got to be in there, things are happening. It had to spread those apart. So at some point, we had extra energy in there doing something. There has to be some type of activation energy. So this energy here, that's our difference in energy. That is my EA, my activated energy, sometimes referred to as Q. And really, this is just a probability. We could have something that is, e to some power of the activation energy over kT, where K here is Boltzmann's constant, T is an absolute temperature. And this gives us some type of probability of this happening. And it is going to be dependent on temperature. The more heat that we have, it's going to increase the probability of this happening. All right, so moving on from this one, kind of combining these two ideas of Fick's first law and this activated process, we have the Arrhenius relationship for diffusion. Remember that D that we had in Fick's first law, or diffusivity. So D equals D naught times e to the power of negative QD over RT. All right, now this is not linear. This is not like Fick's first law. This isn't linear, and the reason we know it's not linear is because I have this exponential term, which is not linear. Before we kind of get into that, I just want to write some things off to the side here. D is, again, that diffusion coefficient, which is area per time. So I'm just going to write over here that this is something like meters squared over seconds. I have my D naught, that's my pre-exponential. And this, again, is going to hold the same units as the answer. It has to. That's why it's there. At least one of the reasons why it's there. QD is my activation energy, and it is going to be something like joules per mole, or on the really, really small scale, we could be doing something like electron volts per atom. And now T is our absolute temperature. We want to use an absolute temperature scale so we don't have our negative up here in our exponent. So we're going to use Kelvin here. All right, so one important thing, and this goes for all sciences, engineering, physics, chemistry, you're going to get data sometimes and you're going to have to explain it and figure out what's going on. That's easy when it is, or relatively easy, it's simple when we have linear relationships. When we have things that aren't linear, it does get more complicated. So sometimes what we have to do is we have to take this, fit a line to it, and then we have to figure out how to linearize it. And that's what we're going to do here. So we can really understand it, we're going to linearize this data. What I'm going to do is I'm going to multiply this entire thing by a natural log and take the natural log of the not multiply, I'm going to take the natural log of this entire thing. So I have the natural log of D on one side, I have the natural log of D naught e to the minus QD RT. All right, I can do my logarithmic rules. I can break this apart. ln D naught plus ln e minus QD over RT. All right, simplify some things again. I like to do things step by step. I'm trying not to just mix steps here for you guys. That is my D naught plus my natural log and my exponential. Technically, you could say they cancel each other out. They make each other go away. So I just end up with negative QD RT. I'm going to rearrange and pull out. I'll go ahead and pull the negative sign out too. So I have the negative sign here. I'm going to end up with QD over R, and I'm going to multiply this by 1 over T. That's going to be my independent variable. All right, so what I'm going to do is now I'm just going to take this whole thing. I'm actually not going to do anything to this except for rearrange it. I'm just rearranging it so that it looks a little bit differently. Really all I'm going to do is I'm going to take this, the negative term that's on the right, and I'm going to move that to the left. I'm just going to swap places here. So I have negative QD over R, the 1 over T times 1 over T, and I'm going to add my other term here. Now, why did I want to rearrange it this way? I want to rearrange it this way so that I could easily match things up. And what I'm going to match it up with is y equals mx plus b. This term here is my b. This term here is my y. This term here is my m, or my slope. And here I have my x. Well, what I can do then is I could actually plot my data with this new equation. I could have on my y-axis is going to be ln d, and my x-axis is going to be 1 over t. And as I plot things, it's going to have a y-intercept, and that y-intercept is right here. That y-intercept is going to be ln of d naught. And I have a slope here, and this slope is going to be QD over R. All right, so that's just a little bit of math. We might linearize some things later on in the quarter, so that might be something to keep in mind. Real quick, just to finish up, why do we care about diffusion? Really, diffusion happens with everything, and so it is important. There are some things where we see it a little bit more, such as containers that are holding pressurized gas. We have high concentrations of something, we're going to see that diffusion. Hydrogen embrittlement. When hydrogen diffuses its way into a lot of materials, it gets brittle. The material starts to break down. And so that is important, understanding how that diffusion happens. And also maybe changing surface concentrations, such as case hardening in steel. The idea here is, and we'll talk about this when we get into properties a little bit more, if I have some steel here, this steel might be kind of a soft steel, and I don't want it to be soft. I want it to be hard. I want it to keep its shape. But when I make it hard so that it keeps its shape, it also gets brittle, and I don't want it necessarily to break either. So what I could do is I could make sure that the surface has more carbon in it than the middle. The middle is going to have a little bit of carbon, but not as much. What that's going to do is it's going to make the surface really, really hard. It's going to keep the middle more tough, but it's maybe a little bit more malleable. And now why would we want to do that? We're trying to exploit two things here. If I have to make something like, let's say, a gear that's going to have a lot of force put on it, I don't want those gears bending. I don't want a soft material that can bend, but I also don't want the teeth breaking off. I don't want it to be too brittle either. Maybe if I'm making a file or a tool for machining or something, I want it to be hard so that the tool keeps its shape and can do its cutting, but I don't want it to break constantly. I don't want it to be too brittle either. I want some toughness, and so we can keep that middle a little bit more tough so that the tool or file or gear or whatever it happens to be won't break.